Hi everybody, my name is Tjomme Doper. I'm here to present the results of my master's thesis at Eindhoven University of Technology, supervised by Pascal and Alex, who are here today, and in collaboration with ASML, who is they make machines for the semiconductor industry. And it's on using product complexity to forecast learning curves in manufacturing cycle time. From the past couple of days, I'm assuming most of you have an understanding of what product complexity means, but let me start by explaining what a learning curve in manufacturing cycle time actually is. So a learning curve is a phenomenon in which a company improves its performance upon producing more and more units of the same product. So in cycle time, that means the cycle time for a single unit, the time that it takes to produce one unit, actually goes down as more and more units, cars, laptops, whatever, are produced. These curves, they have a starting point for the first unit and usually a limit or asymptote because there's a limit to the time, to manufacturing cycle time. And what companies usually see when they introduce a new product version is that cycle time goes back up again and a new learning curve starts for this new product version. Because the factory has to get adjusted to this new product, there need to be new processes, maybe new tools, employees need to get adjusted to a new way of working. So that's why cycle time goes up when introducing a new product version. And the challenge for this thesis was, can you predict what this learning curve of a new product is going to look like before it actually hits the factory floor, right? So to predict, this learning curve in manufacturing cycle time for a new product version, given the cycle time for the old product. A quick note on quantifying complexity. So this is the metric I use to quantify complexity. It was developed at MIT a couple of years back by a PhD student. It breaks down complexity into complexity of the components of a product, the complexity of the interfaces, and also the complexity of the structure or the architecture. A quick example, here you see two products with the same amount of components and interfaces, but the one on the left has a centralized architecture and is therefore less complex than the one on the right. I started out with a simple experimental study in which a group of people, actually two groups of people, assembled a simple machine made out of Lego. So there were two variants. One is simpler than the other, and both groups made both variants, but one group started with the simple variant, made it 5 times, and then moved on to the more complex variant. And the other group started with the complex variant and then switched to the simple one after making it 5 times. And the most important conclusion I drew from this small study was that learning carried over from the simple product, from the complex product to the simple one, but not the other way around. And the explanation I found for this was that the complex version, I'll show it again, is basically an extension of the simple version, right? So it's very similar to the simple one with some extra parts added on top of it. So this led to to a forecasting model based on 2 fundamental principles. The first one is that product complexity increases cycle time, which is not that far-fetched, I hope. Second principle is that the complexity of only the new and unique part of the new product causes this jump in cycle time between 2 product versions. So to illustrate, here you have cycle time for some product, a learning curve split up into 2 parts. One part is attributable to the common architecture between both the old and the new product, and the other part is attributable to only the unique part of the old product. Now, upon introducing a new product, the jump in cycle time is fully caused by this unique new part of the new product. So we can get an estimate of this jump by computing the complexity of this unique part of this new product. And then we can also get an estimate for the limit of the learning curve of the new product. Since we have the cycle time data for the old product, we can fit a curve and get its limit or asymptote related to the complexity of the old product. Since we have the complexity of the new product, we can get an estimate for the limit of the learning curve of this new product. And with the starting point and limit of the learning curve both defined, the only thing left is to figure out how quickly the learning curve moves from this starting point to this limit or asymptote, and that's what's called the learning rate. And for now, we assume this learning rate for the new product is equal to that of the old product. So these three parameters, we have a learning curve fully defined, and this is basically the forecast for the learning curve for this new product that is not in production yet. Just to give an example, here is how all of these parts of architecture relate to the Lego model I built. So here is the simple machine with its DSM. Here's the complex machine and its DSM. And here's the DSM of only the unique part of this simple machine. Here's the DSM of the unique part of the complex machine. And then finally, this is the DSM of their overlap in architecture. Well, this is all good and well. It's a nice toy example to develop a model. But of course, in the end, we want to be able to apply these types of forecasts in a real world scenario. So I also did an in-depth case study, and I'll spare you the details, but this is the cycle time data that I obtained. And what we see here is two versions of some product being produced, and there's a cycle time. The new product is introduced at unit 36. So you see a clear jump in cycle time there. And then using the cycle time data for the old product, here is the forecast for the cycle time of the new product in yellow. So in blue, the actual data, and in gray, a naive forecast, which basically takes the learning curves of the old product and uses that as a forecast. And you see that the model I introduced basically improves upon this naive forecast by increasing the starting point, because the overlap between both products was relatively small. It was a very large and complex new piece of architecture that the factory needed to understand. And also the asymptote is lower because the new product was actually less complex than the old product. So in conclusion, using this model, giving an existing product and its learning curves in manufacturing cycle time, we can forecast the learning curve of any proposed successor, given that its design is sufficiently defined. All right, so thanks for your attention, and I'll be looking forward to your questions in the comments.
Thank you very much, John, for this very insightful presentation. Interesting. Thank you.
You're welcome.
Nassim, are you still there? Do you want to try again? Yeah, I make my words. Those are the William on the chat for you, John. Very nice work. Very clear presentation. Nassim, are you there? No, currently not. So we're moving forward to the third one. Let's see if we can solve the technical problem with Nassim. So the third presentation is from Julian Grove. It's an industry presentation.
All right.
And if you're ready, Julian, you can share your screen, and the floor is yours.
Sounds good. Just a moment. It's in window. Well, good morning from the west coast of Canada.
Yeah, we're not seeing your screen yet.
Okay. Yeah.
Okay. Now it's coming.
You see the
yeah.
Big
now we see it.
Screen? All right.
Yeah.
Perfect.
Go ahead, Julian.
Thank you. All right. So yeah, good morning from the west coast of Canada. My name is Julian Grove. I'm one of the senior systems engineers at Starfish Medical. And today I'm presenting a case study on behalf of Mike Stowe, Frank Waldman, and myself that we've called Re-Architecting the Winnipeg Ventilator for Efficient Change Proposals. This case study was spawned out of preparations for the industry sprint workshop for this conference. But when the conference moved entirely online and the workshop was canceled, we decided to pivot those preparations into this presentation. The content and the case study is based on a simplification of the Winnipeg ventilator program that Starfish Medical executed on behalf of the Canadian government in response to the COVID-19 pandemic last year. So I get the pleasure of presenting some real world data in a sort of a post-mortem format for this project. The ventilator development and manufacturing program was initiated in March 2020 with rapid progression to a final design review in July 2020, and then submission to Health Canada for review and approval in parallel with production ramp up to full-scale production of ventilators by October 2020. Now, Starfish Medical is brand new to DSM. We could measure our exposure to these tools and methodologies in the order of weeks. And so as we set out on this journey, we asked ourselves, what can we learn about DSM tools and what value propositions can we identify in the DSM methods and outputs to leverage on other projects in the future? So that's the focus of this presentation. But before we get to those lessons learned, I want to share a little bit about the product, people, and process architectures that we analyzed. So starting with the product architecture, you say, well, what is a ventilator? What is the Winnipeg ventilator? So its function is to take in air and compressed oxygen, mix that together, and then supply tailored breaths to critically ill COVID-19 patients via the breathing circuit. To enable this, we implemented a modular architecture consisting of 7 different modules. At the top, we had the UI module for control inputs and operating parameter feedback to the respiratory therapist. We had an IO module for power supply and management. We had the main PCB, which is responsible for all of that power distribution, sensing, and control, including running the embedded firmware that operated on the microcontroller. And then below that, within the chassis structure, we had the pneumatics module that handled all the gas direction and pathways, taking in the supply gases, transferring that down to the piston pump, where it was mixed and then pushed forward on a breath by breath basis, back out the pneumatic module to the patient. All of this was held together by a wheeled chassis, making the device mobile to move around the hospital. When we take a look at the DSM for this device, we can see that clustering groups the product into 2 sort of main clusters with highly coupled system, with the chassis and main PCB being the key change propagators, not surprisingly, given their influence to the mechanical and electrical domains. From a project plan or process architecture perspective, we simplified the actual execution to a phase gate approach over the tight timeline. The dependencies between the modules in their design within each phase were not reflected to make this as simple as possible. And an early as possible sequencing algorithm was applied to show no planned iterations in the DSM on the right. The final stages have dependencies to the product architecture where we build and test each of the modules and then integrate. From a people architecture perspective, the teams were split into 7 module teams and 1 integration team. And then the roles were assigned to each of those teams based on the engineering discipline requirements to produce a given module. Dependencies in this domain were inferred from the dependencies within the other domains and the marked dependencies between the domains. When we apply a spectral clustering algorithm, we see 2 main clusters form, 1 mapped to the product domain, 1 to the integration domain. The strength of the dependencies shown here relates to simple count of dependencies across the domains. This helps to identify which roles are most important to the success of the project. In terms of the dataset flow, we were able to take the Winnipeg ventilator system architecture document that we produced last year, translated that into an industry challenge dataset inputs workbook with a section for each of the 3 domains. And then that data was translated into a format compatible with one of the DSM symbiotic technologies, in this case, LaTeX. And that was used to produce the DSMs and analyze them as shown on the right. So what have we learned so far, newbies to the DSM world? Well, we know that DSM setup requires significant effort to model the relevant dependencies from subject matter experts, even in this relatively simple postmortem example. And we recognize that there's dynamic evolution of the design and team before a model becomes useful. So starting too early could lead to unnecessary rework. And finally, perhaps most importantly, DSM provides a concise visual representation of dependencies within and across complex architectures. To carry through the Industry Sprint Workshop Challenge, we tackled two design challenges or real issues that were encountered on the project. The first had to do with oxygen intake and mixing accuracy that we identified during design verification before the final design review. To summarize, the performance of the ventilator was insufficient to demonstrate safety and efficacy of the device at that time, and improvements were needed. The second issue was found in the piston pump, where the position feedback sensor produced an unexpected artifact resulting in rapid piston movement and tripping of overcurrent protection. So we had to explore a solution during the early phases of production ramp to that challenge. So the Industry Sprint Workshop task would have been to analyze the product, process, and people architectures for the impact of the two issues and to identify and propose corrective actions. In this case, we dropped off the identification and proposal of corrective actions, having already been through that ourselves last year. The first impact analysis looked at the oxygen intake. And to do this, we used the impact report functionality built into Lattice, selected the affected element of the system, and then ran the impact report. This tool very rapidly illustrated the trace of dependencies from the affected element through the direct dependencies at level 1 to the subsequently linked dependencies in level 2 through 11. What this allowed us to see is who was affected by the change in terms of the team, what was affected in terms of the components that are either directly linked or subsequently linked to that component, and then where in the process this has been encountered. If we were to dig into this further and had used this in the actual project, it may have helped with rapid deployment of teams to help address the issue. The second impact analysis had very similar results in terms of the breadth of propagation of the impact, but we came to realize a second key takeaway, which is that when we identify where in the process step this issue has occurred, even if there is no marked feedback loop dependency, that could be added and the subsequent iteration could be propagated from the DSM out into project management tools to help understand the timeline and project impacts of that feedback loop, including running a variety of different scenarios as needed. So what did we learn from the impact analyses? Well, for the most part, the reports matched what we experienced in terms of the key impacted elements, so there's no surprises there, which is good. It also enabled rapid assessment of the breadth and depth of an impact of an issue and allows us to visualize what is affected and who is affected and what the process feedback loop looks like to resolve the issue. To very quickly summarize again, DSM approach requires significant effort to map relevant dependencies and build the model. While there's dynamic evolution of the design and the team before the model becomes useful, it can provide significant benefit, including concise visual representation of dependencies within and across complex architectures. And when unplanned change occurs, the model can quickly identify the breadth of the impact in terms of product and people and the necessary rework path for corrective actions. So I'm excited to take this tool and see what other applications we can find for it at Starfish. Thank you.
Thank you very much, Julian, for this presentation. Yeah, everyone's clapping hands to you, which it says it's a continuation of the keynote we had on the first day, and now we're seeing how the DSM is being applied to the product that was presented to us 2 days ago, and I think that it's been clarifying for a lot of us on the power of DSMs for doing this kind of analysis. I think for you as well, you are learning that at the same time. So thank you very much for this presentation. Let's move for the next one. We still have the problem with Nassine. I don't know if Nassine is there, but I propose that we move him to last. So now the next one on the line is Leonardo Manzioni. Another industry presentation. Leonardo, are you there?
Yes, I'm here now. Okay, just a few clicks. Let me close some windows. I think you don't want to see my email, okay? Okay.
Whenever you're ready, share your screen and.
Okay, it's everything closed. Okay, let me share my screen and let me open my chronometer. Only 12 minutes. Oh, I have to resume 40 years of experience in only 20 minutes. I'm teaching DSM, yes, for 15 years. I'm the first Brazilian research in DSM. My master research is the first one in Brazil. I am the first researcher that studied and teach DSM in Brazil. Okay, it's important to note this for everybody. Let's move my camera. I think here is good. Okay, now it's good. On the center. Okay,
we're still not seeing your screen.
I'm okay. Let me share my screen now. Fabiano, are you Brazilian?
I'm Brazilian. As we can speak in Portuguese later.
Oh, very good. Very nice to see you. Nice to meet you. Okay.
Nice to meet you too.
Let's start it. Could you see my screen?
Yeah, we're seeing it now. So you may start.
Okay, let's start. Let's open the time. Okay, time go. I will present this theme. The name of my presentation. It's about why is design deliver always behind schedule. It's a critical review of the design planning techniques used on the AEC market. Okay. It is basically a summary of conclusions based on 40 years of experience and case studies in building design and management process. Well, as I say, I'm the first researcher in Brazil. I studied DSM, and I am very enthusiastic about the DSM. Okay, so let's go to the conclusions. The common misconception: professionals plan design building based only on the control of the final deliverables, drawings or BIM models. They do not focus on the design process and its management. Companies hire projects using delivery-based model. The professionals plan the design on the same way as the constructions, using only paired CPM and Gantt charts. It is the reality. Only Gantt charts cannot represent the characteristics of the design that are cyclical, iterative, information-based, collaborative, and involving numerous teams that must work simultaneously and collaboratively. Design works different than constructions. Design is a non-linear process. It involves a complex workflow composed of progress phase, decision points, and rework loops. Information is the design field. So, To plan and control the design, I use this like a mantra to my students and my clients. This key phrase: follow the information. If you follow the information, if you follow the trace of the information, you manage the project. Not manage a project based only on the deliverables, because we are not in construction sites. No, not confusing construction site with design management. It's totally different, okay? Root cause, some, of course, there are a lot, hundreds of causes of design's rework. These are basically intrinsic coupling between tasks. Poor sequencing tasks organization, incomplete tasks, information missing, incomplete or wrong information, lack of decision by the owner of the building, owner of the project. The decisions are made at the wrong time sometimes. Information arriving late. There are many changes, constantly changes in information input. Design a building is much more complex and harder than design or construct an airplane, okay? Because construction are unique, are very different. Each construction you have to build a factory and all a supply chain to build one build. And in the automobilist or aeronautical, you build a factory, a plant, and the product goes. In construction, the factory, in automobilist, the factory is still at the same time, and the product goes through. And on construction, you construct the building, you make your factory, and the factories go. It's just the difference. It's totally different. Some issues related to information flow management. Of course, there are many others. I will cite only these 4 principles. I don't want to read everything. I think you share the slides or record the presentation. But basically, we have lack of design, systemic vision of design professionals is very perceptive. Lack of information availability, twisted information, too much noise in communication, bureaucracy in information transmission, simplistic information, very hierarchical, actors on the process, much confusion. Lack of feedback, lack of understanding of decision, lack of everything, lack of awareness of information history, lack of awareness of how information is applied. Interpretation of information has many problems. Information is communicated many times with ambiguity. Yes, I think 50% is based, our research are based in communication. So you have to think about information and communication to solve problems of design management and to improve the use of DSM on software markets. And finally, I cite here some issues related to software tools. I think the existing software in the DSM market has not yet effectively discovered the possible integration between DSM and BIM models. We have very few software dedicated to process architecture models in the AEC area, because in the AEC we operate with process architecture models. The tools concepts are based on rigid and bureaucratic work breakdown structures. Rigid structures, excessively hierarchical decomposition of design activities. I think the critical path method is CPM is not necessarily the biggest or best criteria for analyzing project schedules. There is a lack of graphical tools for design process creation and analysis using BPMN or business process model and notation. Lack of interoperability with commercial software like Microsoft Project and Primavera P6. These software are in native formats with no interoperability between each other. There is a need for a creation of open standards. There's no open standard. High price, expensive softwares. There's a lack of good documentation, helps, and tutorials, simple tutorials. And we need software as a service model. I think it's not yet a reality in the design process plan. So what do we need in a DSM software? Some things, flexible and simple, graphical interface and direct interpretation of BPMN files, integrated to process, BPMN, DSM, and schedule, interoperable with commercial softwares like Microsoft Project, Primavera P6, Asta Power Project, and so on. Integration and capturing information directly from BIM models in IFC format that is an open standard on the construction industry as a building smart standard. Follow information and constant change on the fly. Cloud-based and with software as a service subscription mode. That is, I think we need this. We don't have this yet. I'm make some site testing with site of LaTeX with Frank Waldman, and I am a beta user, beta tester, and I make my own research and tests, and I'm stressing this software. I'm very stressing all the possibilities and some findings. Frank Waldman has presented this slide. He borrowed from me, and he presents first. I think you have, you saw the Frank presentation. I will not repeat, okay? But it's the same thing. We can rapidly, fastly architect the process, create diagrams, import into LaTeX sites, partition with DSM, export to Microsoft Project Primavera, complete detailed design in MS Project, and I recommend not much detail, not detail with much information, only you have to think the level of information you need, just this, not much, not minus. Execute the project, of course, and capture the changes when an unplanned iteration is needed, mark the PD dependence in like site on the fly, and automatically an iteration group is inserted on Microsoft Project. This is BPMN file. It's very new. This graphical interface is very new. It's all in BPMN notation. Here you can build a process from scratch, or even based on a template, and site captures this, automatically capture this information and convert this to your work breakdown structure. And of course, you can mark this on DSM. Automatically, DSM is constructed based on BPM file. So the data input is very simple and fast, okay? Very simple and fast. And so you make the partition, and here you can see a Gantt chart on site, simple Gantt chart, but I think we don't need much more. But Some people want to work with Microsoft project, Primavera, Asa Power project, and so on. And we are make this interoperability to be real, not closed. We don't want closed software. We like open software. We love open software, open stand. I am being open being guide, okay? Open being guide from Build Smart from Brazil. And here you can turn, you can make turn here. And finally, you export this to a Microsoft project, and you can work in a day-by-day basis. Okay, and finally, this is my book. This is a new book, and in this book, I have a chapter only dedicated to DSM software, and my book is based on ISO 1965. It's very new in Brazil. And another thing important, the presentation of my book was made by Professor Rafael Sachs, the top one researcher of being on the world. Okay, I want to show you my book, my email, and okay, all the time, 1 minute left, 1 minute on, okay? Okay, Fabiano, it's very good.
Yeah, great.
Thanks.
Congratulations.
Thanks, people. Questions? Thank you. Thanks for all. Okay, stop sharing here.
Yeah, there will be a question when you're going to publish this book in English, because in Portuguese there's only a couple of people here in the conference who can read.
Yeah, yes. No, we are working. No, yes, we just have an English version. Is ready, and we are my partner, Professor Silvio Melhado, works on Canada. Okay, he teaches on Canada, and we are negotiating the rights with the Canadian companies and also in the UK. He has some contacts in UK, and now is the time you are negotiating royalties and rights and some adaptations to the culture, to the local culture. Brazil, the construct different than England, and England construct different to the USA. Okay.
That's just a final remark. Thank you very much. So now let's move to well, actually, it's the last presentation from our schedule, but then we're going to go back again for the first one because we think we have solved the problem. But now I'll give the floor to Jana Rovar, who is going to present her student poster. So Jana, whenever you're ready.
Hello, everyone. I hope you can hear me clearly and see my screen.
Yeah, we see your screen, we hear you. You may start when ready.
So it is my great pleasure to present my student project at this DSM conference this year. And my ongoing project is entitled as Support of Ontologist Integration for the Interfaces Analysis using DSM-based approach. As nowadays, there are no computer-based support for product design that could cover all stages of product lifecycle, or at least to provide links between tools that are applied to early and unstructured design problems and tools that are used at subsequent stages. Even though PLM has been aiming to support the complete product lifecycle, it has always been very focused on the detailed product development phases and has failed to properly manage the complete life cycle of the product itself. And in order to achieve effective digital engineering solutions, it is necessary to solve the problem of integrating product lifecycle management and model-based system engineering domains. And such integration should enable design teams to have a digital data thread for the product development process. Indeed, design processes are supported by a variety of ontologies representing each of the domains, and there is no clear methodologies or tools to manage and analyze interfaces to avoid models inconsistency. And since none of the ontologies is sufficient on its own to describe the complete life cycle, successful data exchange can be realized through the integration of ontologies that underlie the application used by teams in the design process, representing each of the domains. We address this problem by proposing digital engineering methodology. So this DSM Sorry. For some reason I stopped sharing. I'm sorry. So this DSM representation of the proposed basic ontology of digital engineering built on the object process methodology, that is the formal ontology of object, processes, and state entities, which allows a system designer to effectively represent a complex system of any nature, its function and behavior, and particularly it is used at the conceptual design level. The second level of integration is engineering system, which includes behavior and function entities that are represented in core product model developed by NIST and supplemented by entities necessary for proper product definition, for example, such as product geometry tolerance that are absent in CPM. But this entity is critical to product definition at the detailed design stage. And the third level of integration is manufacturing process management, which represents the transition from the 3D geometry to the complete manufacturing process definition. So all these three levels of integration are absolutely required to complete the digital thread for the physical and digital twins. And to address the semantic integration problem of ontologies, we adopted the following approach for defining the types of relationships between representative ontologies and each sets of entities that they include in them. We define various types of interfaces between these systems ontologies according to OPM links classification. The OPM methodology is a powerful approach for effectively representing the interfaces of complex systems. So the set of interfaces proposed by OPM methodology can be used to explicitly represent all interfaces within the system. OPM consists of 4 structural interfaces that connect entities with the same persistence to express the time invariant relationship between them. And in DSM, they identified with pink color. Another type of interface is procedural links, which connect processes to objects to express dynamic aspects of the system. And they identified with green color in the DSM. And each procedural link may have each procedural link may be qualified as state specified link that are identified with blue color in the DSM. And the state specified procedural link is a detailed version of its counterpart to a procedural link in the sense that instead of connecting a process with an object, it connects a process with a specific state of that object. And for each type of the OPM links, we assign a designator, which we filled in DSM. So the cells at the intersection of different rows and columns indicate the type of relationship between the corresponding entities. And to provide this mapping, we consider the persistence of entity from OPM perspective, analyzing whether the entity describes only an object, stateful one or stateless one, or a process, or even both at the same time. As a way to represent a digital twin, that translates digital components coming from upstream into physical realities, downstream, and vice versa. We consider bidirectional data exchanges. Thus, matrix elements with the designators below the gray areas indicate the presence of the downstream flow of data. And matrix elements that are with designators above, gray areas demonstrate the upstream data flow going from the physical realities to the digital components. It is also—
Jana,
yeah, sorry.
Sorry to disturb you, but we are just seeing your PowerPoint. I don't know if you want us to look at a specific part, just to warn you that we are just looking at your PowerPoint.
Could you repeat?
I don't know if you want to point us to a specific part of the poster, because we're just seeing your PowerPoint and the poster is not completely on the screen.
Oh.
You can perhaps go back to presentation mode just for us to see the whole poster. Sorry, just you can continue.
Can you see my pointer now?
No. Okay, now we see. Oh, yeah, there you go. Now we see the whole poster. Yeah.
Sorry. I don't know what's the reason. Also important to know that this DSM is not symmetrical, as some types of the links are unidirectional, for example, such as result or instrument links. And this method demonstrates how the ontology of each step of product development is structured with respect to the domain, and that ontologies lack proper attention to interfaces to better understand the fundamental principles and current flows of the digital chain integration. Also, we foresee this method as a way forward towards using integrated ontologies as concrete implementation tool to increase the clarity of digital systems and define mapping rules and significantly reduce the inconsistency. However, as you can see in orange circles, the mathematical analysis of these metrics is complicated in case of several interfaces appearance between two entities. That is why the hypothesis that I'm working now and that I suppose would lead to the concrete tool development is improvement of complex systems development through three-dimensional DSM models. So to facilitate the further analysis, I propose to apply three-dimensional DSM approach that looks like the division of the integrated DSM into layers according to link types. And here we have the representation of three layers dedicated to structural, procedural, and state-specified links. And further, we can represent this 3D DSM as a multidimensional array to provide some computational analysis. And to conclude, we foresee this methodology as the basis for building tools to better interface management of complex systems to provide a translation of OPM model to engineering system model through the integrated DSM. That could be implemented through the extraction of CSV file of OPM model, further mapping of each model, entity, and relationship through the integrated DSM of ontologies with entities and relationships of engineering system model. So thank you for your attention. I'm ready to answer your questions, and any feedback from your side will be extremely useful for me. Thank you.
Great, Jana, thank you for your presentation in time and very interesting. Okay, we still have one last presentation. Actually, it's the first that we skipped. I was informed that Sonia Kerbaki is going to present replacing Nassim that is having technical problems. Sonia, I see you there. Are you ready?
Yes.
Okay, so whenever you're ready, you can share screen.
Okay.
And thank you for backing up your colleague.
Are you seeing my screen?
It's coming.
Okay.
There you go. Yeah.
Okay.
You may start.
So evening, everyone, and thank you for letting us to show you our work instead of Nassim, who got some issue. So our presentation is gonna present supporting sustainable manufacturing practices implementation using design structure matrix in the Algerian economy. And for doing this, now I present our findings on sustainable manufacturing practices implementation by presenting the research motivation, and then share with you our proposed model. And then we will discuss the research perspective and the results. Today we'll be covering these three key points. What are the common sustainable manufacturing practices that contribute to successful implementation? And the second key issue is what is the most policy that influence the successful implementation of sustainable manufacturing in our country, so in Algerian economy. And the third one is what are the strategies implicated the application of sustainable manufacturing practices. And these three main questions will allow us to identify the most relevant motivation. So that pushed us to treat specifically this issue. So with the main goals of reduce zero damaging impact on society, environment, and economy, we proposed to solve this requirement. So ensure sustainable manufacturing implementation success, understand the practices that are needed to implement sustainable manufacturing in our economy, and exploring the stages of sustainability issues in Algeria. These 3 layers are selected, relied on the United Nations 2030 agenda based on SDGs. Our proposed model is made on 3 layers, as you can see here. Sustainability strategies. The second layer is the policies the government use to express the sustainable strategies, and the sustainable manufacturing practices on the level of SMPs. So the first layer is made up of the adopted sustainable strategies, such as you can say business waste or social well-being. And secondly, the random walk simulation. As you can see in the layer, we present that a random walk strolls in the constructed object user network. So they jump from one layer to another based on their interconnection or interdependencies. And the interconnection between these 3 layers presented a set of indicators that's characterized by these 3 matrices. So we have addressed the design structure matrix method to explore policies promoting sustainable strategies. And this model can be divided into 3 blocks corresponding to the 3 chosen layers that I present just in front of you. So the policies DSM is conducted by the policies SMEs influence matrix, and the policies sustainable strategies, this one on the right, and on the left for sustainable manufacturing. So the basic idea of the method is to simulate the process that a random walker wanders in the policies network. So from this matrix, and in the random, the policies is expressed as the dependency between 2 policies with the probability of the random on the network. And in this presentation, we will analyze the Algerian manufacturing sector to verify the concepts and model. The purpose is to reveal how Algerian policies support the implementation of sustainable manufacturing practices. The choice of this case can be justified by that Algeria has not robust guidelines that ensure sustainable manufacturing implementation. So available literature defeats to consider such a complex research topic from the triple bottom line perspective, social, environmental, and economic. In addition, no studies are exploring the status of sustainability issue in the Algerian economy, which justify the study geographical focus. The Algerian state sheds light you can say 3 principal policies: trade, industrial, and innovation policies. So the Algerian government strives to confirm that trade policy help promote sustainability. Oh, sorry. It should be here, the matrices output, but I don't know why it doesn't present well here. So you can see here the rank by row and the rank by column, and the final rank to see how the policies made in Algeria are most important than others. So the support offered by innovation policies comes down to the significant role that innovation plays in the Algerian industrial sector, since innovation holds a central place in the government. And as original work, this study fulfills its research goals while providing a fulfilled roadmap to more helpful research on sustainable manufacturing practices implementation. And such a result led us to propose future perspective to consider an unspoken research where additional needed efforts have to be done, considering other policies to explore further implementation of SMPs and in developing economics, such as R&D policies, monetary policies, or technology policies, and so on. And that brings us to the end. So we sincerely appreciate that we have had this opportunity to present with you, and we welcome you to ask your question regarding the random walk theory and this use in DSM network. So thank you.
Thank you, Sonia.
To give you a summary, because I didn't know that I will present, so I just have a summary of the results.
Yeah, totally understandable. Use half of your time, but since you were backing up your colleague, it's totally understandable. Okay. Thank you. At least we had a presentation and we know what the paper is about. So thank you once again.
Welcome.
So now we have gone through the 5 presentations. We still have, we have 15 minutes, right? Yeah, we have 15 minutes for the discussion, which is very good, in spite of all the technical problems we had in this session. So it's good news.